Hi folks, this is Bass Action Back in Action here, and on this page of notes we are going to do a comparison and begin to look at the difference between average rate of change that we did in the previous video and instantaneous rate of change. And our instantaneous rate of change is actually going to come in the form of our difference quotient that we did the other day. So the other day we were practicing our difference quotient and we were just practicing the algebra with it. Okay, so here's our difference quotient and we're going to practice again working with our algebra, and then we're going to apply that so that you can understand a little bit more how the difference quotient helps us. I mentioned the other day that the difference quotient is going to help us lead to this idea of a limit, and later in your calculus classes, then the idea of a derivative. So taking a look at the graph that I've provided here on the right, the first thing that I want you to notice is that there's a red line here on the video here. There's a red line here, and that would represent the secant line that we did on the previous page. Okay, so our secant line is going to go through our graph twice, and it will approximate the rate of change along this graph. Okay, so about how steep is this portion of the graph. Now, the idea of an instantaneous rate of change is what we're going to do is we're going to imagine these 2 points moving closer and closer and closer together. So you can see I've got another couple points right here. So I could imagine instead of them being here and here, I then have them here and here, and then here and here. And as they get closer and closer together, it's going to give us a different looking line. And you can see these x values that I have down here at the bottom would be, let's say, our first x value. This one, looking at our difference quotient formula, is going to be this f of x. This other point, this second point, is going to be our original x value plus some value for h. That's where this f of h, f of x plus h in our difference quotient formula is really coming from. So what we're ultimately going to do is we're going to imagine these 2 points, some point plus another point that's farther away, and then we're going to let this h value get smaller and smaller. And as it gets smaller and smaller, our point is going to move closer and closer to our original point. So let's look at the algebra on that and how that's going to help us. So jumping into our algebra and our difference quotient, you'll notice that this equation that we're going to work with on this page is the exact same parabola that we were working with on the previous video. So we can extend that same idea. If you didn't watch that video, you might want to go back and watch the video and how we did our average rate of change. So jumping into our difference quotient, the difference quotient, of course, says that we first need to evaluate f of x plus h. So in this case, we're going to have our -2. We're going to have our x plus h quantity squared plus, remember the x plus h has to go everywhere we see an x, so I'm going to do an x plus h again. Then I'm going to subtract the entire f of x function, parentheses, remember, very important here, minus 2x squared plus x. The entire difference quotient is, of course, divided by h, and ultimately we want to try to cancel that h. Now we're going to start some expanding. So as we begin our expansion here, we're going to have our -2. We're going to expand our x plus h quantity squared. That's going to expand to an x squared plus a 2xh plus an h squared. Then we're going to have our plus our x plus h. We don't need that parentheses anymore. We're going to distribute our negative. Distributing that, I'm now going to have a plus 2x squared minus an x. Now I need to distribute my 2. We're going to distribute that. I do also remember that this entire thing is divided by h. So distributing my 2, I'm now going to have a -2x squared minus my 4xh minus a 2h squared. Then I can just rewrite the rest, plus x plus h plus 2x squared minus x, all over h. Now let's start some canceling. I can see that my -2x squared here is going to cancel with my positive 2x squared here. I can see that my positive x is going to cancel with my negative x, and I'm left with a negative 4xh minus 2h squared, and I'm left with a positive h. So let's rewrite this so that it looks a little bit better for us. I'm going to have my minus 2h squared. It's always best to write it in our descending degrees. So minus 2h squared minus 4xh plus h all over h. Now I can see that my h will factor out, which was our whole goal. So I'm going to factor out that h. And I'm going to get my negative 2h minus 4x plus a 1. Oops. Didn't mean to put my box around that there. Sorry, got a little bit ahead of myself. Let's go back. All right, this whole thing, of course, is going to be over my h. So now my h's can cancel, and I can write my final answer. So I was getting a little bit ahead of myself. Sorry about that. So I have a negative 2h minus 4x plus 1. There's my final answer for my difference quotient. So now that I have my final answer for my difference quotient, what I can do is I can use that to evaluate and approximate some values for h. So this is very similar to what we did in our notes the other day. So up here on part B, we're going to pick a value for h, okay? And we're going to pick a really small value for h. That allows us to make it a little bit more precise, and we can even choose a value for x. What that's going to allow us to do then is actually approximate a slope for a line, similar to what we were doing with our average rate of change on the previous page. So I'm going to have a negative 2, my h value is 0.001 minus my 4 times my x value that I've chosen, plus my 1. So I can type it into my calculator if I want, but I am going to get a negative 3.002. So this is going to be my slope for my line. So this is going to be my slope for my new line that I'm going to graph. Now, remember, this slope is not for the graph that you're looking at in the graph above. This is actually for the slope of the graph that's on the previous video on our previous set of notes. So continuing on in our discussion, what we can see here is that since the instantaneous rate of change is going to be found for a single value, what it's going to do is allow us to approximate not a secant line, but instead the slope of what we will call a tangent line. And yes, that word should sound familiar from your geometry days, because our tangent line is going to touch at exactly one place. And you can see that the ordered pair that I have listed here for you, this 1f of 1, okay, that is the x value that I chose from up above, okay? The x value that we chose in calculating our slope is the same x value. And our f of negative 1, we actually calculated that also on the previous page in our previous video. So just pulling that from the previous video or recalculating it for our function, we would get the ordered pair 1, negative 1. So if I want to write the equation for my tangent line, I'm going to start with my point slope form. So I'm going to have y plus my y value equals this slope that we've just calculated, negative 3.002, and x minus my x value. And then if I want to clean this up a little bit more, I can move everything to one side and expand, and I get negative 3.002 plus 3.002 minus my 1. This would be my point slope form. Remember, we started with our point slope, and we want to ultimately get this into our slope intercept form that's going to help us to graph a little bit easier. So when I get that into its final slope-intercept form, I get y equals negative 3.002 x plus 2.002. Now, for those of you who are in my class, what we're going to do is we will actually open up our notes and we will graph this tangent line on that previous page of notes so you can see that it actually does look like it's tangent to the graph that I've provided. For those of you who might not be my students, if you happen to have or have graphed out that previous parabola, you can sketch that and plot this graph, and you will see that it does look like it's actually tangent to that downward turning parabola. So if this helped you or you have any questions, leave me a comment, and if you haven't already subscribed to the channel, might want to do that. It'll always make things easier for you, and we'll extend our discussion in class. Thanks a lot.